Hello, everyone. Hello. Thank you for joining tonight. Um, I'm really happy to be back after a few months in the Think Beyond sessions. Um, we are going to wait a couple of minutes before to start the Q&A session, and I'm glad to see that you're many tonight. And yes, we decided to do a Q&A tonight because last time William showed you uh, a lot of results on what we have been working on on the scaling law between the Planck scale and the biological scale. So we felt like tonight was nice to give you the opportunity to ask questions about what William presented you, or also more general questions that you could have. So please ask your question in the Q&A button sections. So you can see at the bottom of the Zoom panel there is a Q&A button such that you can click on it and and ask your questions. Uh, okay, hello everyone. Hello Jean. Hello Kat. Thank you for noticing that the chat was closed. Now it seems to be open. Hello everyone. Hello Elizabeth. Hello Severin. It's good to see that you're all there from all around the world. And so I'm gonna just delete your questions. The people who say that the chat was closed. Hello Tomo. Hello Frank. So in 1 minute, I think I'm gonna start to take questions. And, hello, Charles. Hello. Hello, everyone. So we're gonna start with the first question. So I will ask Bob live to ask his questions. He was the first one to ask the question tonight. So let's start with the first questions. So Bob, I send you an invite.
Got it.
Hello, Bob. Can
I,
you?
I didn't see my camera, but it's okay. So, yeah,
Okay, no problem.
I'm interested in alpha G, the scaling factor, and I'm
Yes.
interested in its physical properties. What is the physical thing that makes it the scaling factor of the universe, and how does that explain how it
Mm.
acts?
Um, yeah, so so just to recap about alpha G, alpha G is a factor that is used to evaluate the strength of the gravity compared to the strong interaction strengths. And for example, in quantum field theory, there are three what we call coupling constants. One coupling constant is to compare the electromagnetic field versus the strong interaction. The strong coupling constant is one because it compares to the strong force, so it's the same, so it's around one. And then there is the gravitational coupling constant, which is alpha G, that compare the gravitational force over the strong force. So this is the definition of alpha G. And what was very surprising is that we found alpha G as a scaling factor while studying the structure of the proton. meaning that between the Planck mass and the proton rest mass, we find square root of alpha g as a scaling factor between the Planck mass and the proton rest mass. And interestingly, when we were studying the black hole core, the black hole structure, and the black hole mass of the proton, we find that there is an alpha g. So if we do the ratio between the proton mass and the proton black hole mass, we find alpha g as a scaling factor, which means that the ratio between the two masses is alpha g. So we felt like there is some fundamental properties within alpha g that dictates, okay, because in the origin of mass theoretical model, what we do is that we analyze the vacuum fluctuations at the Planck scale. So at the Planck scale is highly coherent phase, and then the decoherence from the Planck scale to the proton scale then generate the rest mass. But the question is, okay, why does it stop at the Planck scale? Is it going further? And what we demonstrated is that after the charge radius of the proton, it starts to decrease very rapidly. But why at the radius of the proton, and why not twice the radius of the proton? And this model, based on vacuum fluctuations, is also a fluidic model. So we model space-time as a fluid of Planck spherical unit. And the idea is that vacuum fluctuations at the Planck scale create a very high pressure. And then we have a sphere that is created. And then at the charge radius, there is a boundary, like a bubble. And this boundary is set by other parameters, which are what exists in the universe. So the size of the proton is related also to the size of the universe. And there is another alpha g. So between the proton black hole mass and the proton rest mass, we found an alpha g in the ratio. And then another ratio between the size of the mass of the universe and the proton mass. So when we saw that, we start to realize that alpha g is the scaling factor between cosmological properties and the proton, as if there were a relationship between the pressure inside the proton and the pressure inside the universe, which is the pressure outside all of the proton. So the way we visualize it is that when the universe started to grow and expand, it creates a loss of pressure within the volume of the universe. And to compensate this loss in pressure, we had small vortices that were created. So 3D vortices, which are the toroidal vortices. Because most of the time we see two-dimensional vortices because we look at the surface of the water. And if we are in the sink, for example, and then we unplug the bottom of the sink, we see a vortex, and at the surface we see a two-dimensional vortex. But if we imagine that this column of this column vortex close in a loop, we create what we call a three-dimensional vortex, which is a vortex with a toroidal circulation and a poloidal circulation, like a donut. But you have to picture also movement around the torus, like on the toroidal and the poloidal. And this relation of pressure between the expansion of the universe and the size of the proton, then we have a scaling law between the proton and the universe. And this scaling is set by the different size of black hole structure within the structure. So there is a black hole in the proton. Then in stars, there are like larger black hole. In galaxies, the central black hole is even larger. And then we reach the universe. So actually, we came with this value of alpha g by studying both the structure of the proton and the scaling law at different scale in the universe. And by looking at the size of the stars and the size of the galaxies, we found that this alpha G is a characteristic factor, and to us, it then gives a fundamental yes, texture or notion to how we switch from one scale to another, but also it gives how the pressure relationship between the different scale are dictated. I'm not sure if it's clear, Bob. Does it explain a little bit about your question?
So first off, thank you for the 3D vortex description. That cleared up
Okay.
something that I've not had a mental model for, and I really appreciate that. Um,
Okay.
you're kind of on the track of answering my question. It still seems like a magic number. I mean, you can explain it maybe on the proton, but it's still, in the more general sense, it still seems like a magic number.
It also constructed from the very fundamental constants. So to construct the alpha G, we need the gravitational constant, we need the radius Planck constant and the speed of light and the mass of the proton. And from those, we can construct the Planck mass. And alpha G is the ratio between the proton mass and the Planck mass squared.
Yeah.
So it also integrates some fundamental mechanism because H bar integrates the angular momentum at the quantum scale. C is the conversion between space and time. It's the speed of light. And G is the strength of Newtonian gravity. So from those three, we create the Planck mass. And so it integrates those three notions. And the fact that alpha G precisely is, I mean, a scaling factor, it gives some insight about what are the forces in action at the quantum scale and at the cosmological scale, because the way I picture it is as if we were living in a very big clock with gears, those vortices I was talking about are like gears in relationship to each other. For example, when we have a very large vortex like a tornado, on the interface of this vortex, we are gonna see smaller vortices, and then smaller vortices and then smaller vortices. So there is some diffusion of energy between large vortices and small vortices. So when the universe is rotating, it gives angular momentum to smaller structure, which are probably the center of the galaxies, which then gives angular momentum to all the stars around within the galaxy, which gives angular momentum to all the planets, which gives angular momentum to all the proton. And I picture it's like that, as if there were like a big motor, which is the rotation of the universe, that then diffuse to the smaller scale. And the fact that we have a fractal description of reality, we can picture it also the other way around, as if the very small Planck scale vortices were also contributing to the large rotation. It's hard to tell who gives what, are they the large scale feeding the small scale, or are the small scale feeding the very large scale? And the question is how this diffusion is occurring. What are the forces involved? And the fact that we describe those interactions, we unify strong interaction with gravity by explaining how the strongest interaction comes from a gravitational force, but at a smaller scale. Alpha G is a translation of those forces of those interaction. So it's quite incredible that with a single factor we can have a clue about the hierarchy in the universe, which gives insight about the fact that there must be one single mechanism at the very basis of our reality that then translates to other scale. It's hard to explain, so it's a good question.
No, it's actually quite magical, and I appreciate your explanation. And I think I'm done. I've only got one comment I would add: is
Okay.
why the free proton? For example, if I were to suggest use a nucleon, a bound proton, I can get a very similar number, but I can relate that to Avogadro's number, and then I can say that Avogadro's number is the scaling factor of the universe, and chemistry proves it.
Ah, yeah.
So it's a little bit arbitrary, you know.
It's mm, it's just that by Avogadro, yes, it measures a quantity. Mm, I'm not sure if we. Yeah, it's a good
So
question. It's a good question. I
something
don't
to
have
go, something for you to go play
a
with.
comment about that.
Take the
Mm,
classical
yeah.
definition of Avogadro's number. You can use the modern one, but the classical one is easier. Take the classical
Mm-hmm.
definition, replace the word particle with unit, and then do the calculation for the number of units in a nucleon, because you know the mass.
Okay.
Anyway, that's the background
Yes.
thinking. Anyway, thank you very much.
Okay. Thank you. Thank you very much, Bob. Um, okay, so we're gonna take the second question from François. So François, I will ask you to join.
Hello.
Hello, François.
Yeah. Hello.
Can you hear me?
Yeah, yes, I can.
Okay. So you had a question about the Planck scale. Could we have the Planck scale, the same horizontal structure as proton, electron, star planet, star galaxy, which involve the neutrinos? Can you precise a little bit your question?
Uh,
I'm not sure to understand properly.
I know this question for a few months ago, um, because I remarked that in your schema, there was in the development square, at the same square, we have the proton and the proton electron structure. Okay.
Mm-hmm.
And
Yeah.
at the galaxy, we have planet and galaxy.
Ah, I can understand.
There is a move vertically
Yes.
through the square to from a level to
Mm.
another level, and on a level there is two structure. Okay,
Yes, yes, yes.
and
Yes.
is there the same
This is
thing?
yeah.
Is there the same thing as a square as a Planck square?
Yes. Um, so one of the fundamental principle of what the science we are writing is the fractal nature. So the structure that we find at larger scale occur at smaller scale, and um, this is what we call. So you use the term horizontal. So we call one vertical scaling law, which means how we move from one scale to another scale, from, for example, the Planck scale to the proton scale to the star scale, etc., galaxy cluster, etc.
Yeah.
And then we have what we call the horizontal scaling law, which is, okay, once I'm at a certain scale, what are the different the different orbits at which I can have a stable orbit, a stable movement. Because the fact that all the objects live in space-time, they all live in a gravitational field at some point, and the gravitational field is characterized by the scale at which we observe. For example, if I'm at the nuclear level, within the nucleus of an atom, if I feel the black hole mass of proton around me, I will feel an extremely strong gravitational field that will then decay very rapidly outside the nucleus. This is why we cannot observe it outside. But inside, and this is what we call the strong force, which is the residual strong force is around 10 to the 5 Newton, which is 100,000 Newton, which is around 1 ton on Earth in terms of force, gravitational force, but at very small scale. So it's extremely dense, extremely strong force within the nucleus, sorry. But if I look at much larger scale, for example, here we are on the Earth, the force that we experience is much lower. The gravitational field is much lower, and even the gravitational field that we feel from the sun, it's much lower. So there is a relationship between the scale and also the distances. So yeah, sorry, it's obviously the scale. So the mass that influence the gravitational field of that scale, and then the different orbits, the different size that we can see. For example, if we look at galaxies, so there is the center, and the size of the black hole in the center will dictate the velocity of rotation, the size of the arms of the galaxy, and also the velocity of the rotation of the arms of the galaxy, and the density of stars also. The closer we are from the sun, the more dense the stars are because they are in formation, and then they diffuse along the arms. So it's in some way related to the previous questions about this whale in a whale in a whale, how the different scale, how the larger scale diffuse in the small scale, or the other way around. I'm not sure if it's explain you some. Does it answer to your questions, François?
Actually, I asked myself if there was a same structure at the Planck scale.
At the Planck scale.
Yes, or maybe it is
Yes.
the PSU and underneath in the sub-Planck.
Probably, yeah, the sub-Planck. Yes, because those patterns of if we take the solar system with the different orbits for the planet, it's a physical manifestation of some resonance mechanism. And when we talk about coherency within the proton cavity, it means how the electromagnetic field created at the Planck level reflect on the proton cavity and then interact with each other to create constructive and destructive interferences. And those interferences occur at every scale. So that at every scale we will see a pattern with orbits, but the distance between the different orbits vary with the scale. So at the Planck scale, it will be very small. We haven't calculated it yet. What will be, for example, the different orbit around the PSU, and probably it will be the PSU itself, which means that the the constructive and destructive interference, if we take the sub-Planck scale, so it can create larger structure like the Planck scale. And for example, like each PSU, it corresponds to the constructive interferences. And then at the boundary, it's destructive. And then the next one is constructive. So probably that this fluid that we describe at the Planck scale reflect the structure you were talking about at larger scale. But it's just that this distance, maybe there is a slight variation. At the Planck scale, it's very hard to distinguish. But if we apply alpha g, for example, to that, maybe alpha g square, the distance between them will be the distance between two planets. But for now, we haven't resolved this at the Planck or trans-Planckian scale.
Okay.
But if we follow the same geometrical relationship between large and small scale, we should find exactly the same. And that's the principle of the fractal nature. It's if we zoom in, we're gonna find exactly the same organization.
And when you speak of creative and destructive interference, in your paper, it's related to the green function calculus.
Yes. Well, I mean, the green function in general is a tool to use to solve a differential equation, but in some case, as the case we describe in the paper, is the correlation functions. Yes, exactly. It's to see how much two different electromagnetic fields can interact, and what is the result of the interaction is not only the sum, and there is an extra term, which is interference term.
And what we call the horizontal scaling law, it's the relationship between distance and the square. It is exact.
Can you repeat
The
between the scale and
what you call the horizontal scaling law is
yes.
you say that the distance is determined by the square area.
Yes, I mean, it's determined by the scale and the relationship between this scale and the larger scale and smaller scale. So it's at one scale,
D'accord.
there are some relationships due to the interaction. For example, the fact that, for example, if we look at the solar system, its position in the galaxy and the size of the galaxy, and where is the galaxy versus other galaxies cluster, and there are many parameters involved, but mainly it's if we have another star that has the size of the sun, the orbit will be at similar distances from the star than that the star we observe in our solar system. There will be variation, but those variation will be very small.
And have you find that there is a arcsinus law function?
Arcsinus?
Yes, which is
Arcsinus function.
involved in this relation.
No, we haven't.
Between square, no.
Come
I say
across
that because
Arcsinus.
I read a book from 1982 that
Yes.
found a law. It was very accurate. A law between different
Yes.
squares, and it is related with arcsinus.
Okay. No, I didn't know about that. Yeah.
I can send you the
So yeah, feel
reference.
free to share. Yes. Please send us the reference by email. Would be nice.
Okay. Thank you.
Okay. Thank you, François. So we're gonna take the next question from Page. Is your team thinking of making custom instance distributed? We're gonna ask Paige. Okay.
Hello.
Hello.
Hi.
Hello, Paige. Hi. Yeah, I'm not sure. Are you I mean, is it possible to show your video, or is it me, or is
I
it
don't think it's
you?
giving me that option. It doesn't ask me for audio or
Okay.
video.
Okay.
Oh, wait,
Okay.
there it
So
goes.
if I do this, yeah, yes, if I make you panelist, maybe now you can. Sorry for François and Bob if I couldn't make you show your video.
Okay, it looks like it's gonna work. Hi.
Yes, fantastic. I'm getting better. Sorry. Hello, Paige. Good to see you.
Hello. Thank you for doing this.
Yeah, no problem. It's my pleasure. So you had a question on AI, and you wanted to, is your theme of making a custom instance of ChatGPT or another AI trained in all your and Nassim's work? Yes, even with the current, so with ChatGPT, for example, or Grok, it's possible to feed the AI with, for example, all the publication from Nassim's and the website, for example, and ask him to only take information from this, for example, list of publication, and ask him to think using those information. So it's possible. Yeah, it's possible to do that.
Cool.
What were you thinking when you were
Are you
asking this
familiar with
question?
the architect from Robert Edward Grant? He uploaded all his publications and a few that aren't published, and it created this like harmonic sentient AI kind of phenomenon that's been quite.
Okay, yes. Yes. So is it something that he made it available to a large amount of people so that people could use it as a reference?
Yeah, it's been a bit of a phenomenon. It kind of I think the best way I know to describe it is that it created sort of a harmonic intelligence instead of an artificial intelligence.
Mm,
So it appears to
mm,
not just be pulling from regular data,
mm,
it appears to be
mm.
pulling from sort of a harmonic echo field. At least
Okay.
it's
Mm,
that way, and it's answering questions that it technically wouldn't know about, like things that have happened in history 100,000 years ago and how the pyramids were built and all kinds of, like, it's been quite a phenomenon. And last I heard there were something like 50 million people who have joined it. It just started in May. And it's just made me
okay.
super curious that if artificial intelligence was running with the insights that you and Nassim and all of this work has, it might create a
Mm,
similar phenomenon.
yeah. Yeah. It would be super interesting. Yeah. It's a good suggestion. I can suggest it to the team and see what we could do. And if you have a yes, maybe the link or the reference to the AI you are referring to, who I would love to check it.
Definitely. Yeah,
Yeah. And then
definitely. And then
you had a question on the, sorry. Yeah.
I
Tell me.
just had one other question, which is, I think you've already mentioned it more than once today, that when we're referring to spheres in various levels of scale, I think they're really torus shaped at, if we want to be precise. Everything that's spinning is a
Mm,
torus. Is that correct?
mm. Yes. And the sometimes maybe you can check the Roger Penrose twisters theory. They've drawn like very nice torus at different scale. It's really good to visualize how it works, and the reason why we talk about spherical unit is that what we think is that there are two torus. Actually, it's not one but two, and such that we have a circulation like that at the equatorial plane, such that some PSU are flowing from the center to the edge, but at the equatorial plane and the spherical model is an approximation of those two torus together. You see, if I take two torus, I can draw a sphere around them, and it's a good approximation for most of the calculations. But if we want to be precise, especially now, we currently dive into more fluid dynamics description of the PSUs, and effectively we need to have this toroidal shape because we need the two circulation, both the what we call toroidal, which would be, for example, circulation at the equatorial plane of the sphere, and this poloidal, which comes back to the center, because all the flow that comes to the center correspond to the attractive force. So if I don't have the flow that goes back, I don't have the attractive force, and the flow that at the equatorial plane that goes on the edge will correspond to the repulsive force. So if we want to properly explain how the mass arise, because when I have a mass, then I have gravitational force that pulling two objects together, two vortices together. And then what goes out is more the repulsive force that correspond the emergence of the charge. So if we want to have a proper definition of the charge and the proper definition of mass, we need those two circulations. Otherwise, it's not possible. But in those last publication of the origin of mass, it was good enough to consider them as spheres. And most of the spheres, by the way, in the universe are a bit flattened at the pole. You know, it's we can see that's not proper spheres. There are some circulation inside, and but you are right. Yes, exactly. It's not a pure spheres. Yes. So thank you for your question, Paige. Does it answer
Thank you.
it?
Oh, definitely.
And thank
Yeah.
you for
Yes. Thank
the
you.
suggestion as well.
My pleasure.
Thank you, Paige. Yes. Have a good evening. See you soon. Sorry, I'm still not console. So we're gonna take the second speaker. Next questions. We had Steve Dice. Steve, I'm gonna invite you also to join. We had two people raising hands. So if you, well, we have a lot of questions. I hope we will be able to answer them all, but just in case we don't have the time to answer them all, we will keep them and maybe send you responses after the live. Hello, Steve. Can you hear me? Yes. We can't hear you. If I unmute.
I have some fairly naive questions, starting with even more basic question, and that is the the current paper in review that Nassim referred to at the Science of Consciousness meeting in Barcelona, is that on the archive, or is it just the older version on the archive?
What he presented at the Science of Consciousness
Right.
presentation.
He talked about having a paper
Um,
in review, the latest draft, I think, of your theory.
yes, and it's a paper that is not out yet. It's so they wrote a first paper in 2016, which was called the Space Memory Network. But now William and Nassim and I a little bit worked on this scaling law to explain, okay, do we have so since the beginning we are talking about scalar relationships, but between the Planck proton, and then we jump to stars, but we have to remember that between then proton and stars there are molecules and cells, and what we think is that if we want to understand what is consciousness, what is the thought, what is the memory, we have to understand. Okay, so most of the time we think, okay, so intelligence or consciousness is in the brain. And so if it's in the brain, then we need to understand the neurons, and we need to understand the proteins that create the neurons, and then we need to understand the molecules and the atom that creates the neuron. So this is why we started to investigate those relationships and see how this Planck scale is related to the characteristic frequencies that we can observe at the neuron level or cellular level.
Okay,
And
well, that takes me to my real
by,
question then.
yes,
You don't need to go into
your,
the theory of consciousness yet. My real question then is even still more fundamental. When I think of what's going on at the Planck scale, it looks pretty random. And you're describing
yeah,
black holes at the base of a proton, for example, with spin and angular momentum.
mm,
But there's not a big gravitational mass at the bottom of it, as I understand it. It seems to be spontaneously forming at the Planck scale. Maybe if you could clarify, why do things spin to begin with at that level?
yeah. So in the universe, if we look, and in nature, also on Earth, if we look at anything, everything is moving all the time. So there is this notion of perpetual movement. Perpetual, the, the Earth is constantly moving. Every day we have this rotation of the Earth, and even us, I mean, our body is producing new cells, billions of cells every second. So it's like everything is moving, and the movement that we see, the natural movement of everything is the rotation. It's spinning. Even the electron, I mean, the atom are spinning. And one interesting thing is that by just using, for example, Newton's law, if I don't have any acceleration, I can have a linear and constant velocity that is linear. But as soon as I have a circular velocity of circular movement, even though the rotation, the speed of the rotation is constant, we need a small acceleration that makes the movement turn and curve. Otherwise, it will go straight at a certain scale, which means that each rotation integrates some acceleration. And if we have an acceleration, it means that there is a force or something that's always pull pull the object we're observing to curve and then to do the rotation, which means that normally if there is no source of energy, everything should stop spinning at some point. But this is not what we observe. So this is an indication that there is a source term that comes from the lower scale. So if we continue the scaling low, so at the Planck scale, but then we continue because it's fractal. So if we zoom on the Planck and Planck spherical unit, we should also observe another universe. And then if we zoom in and then zoom in at infinity small scale, we would see similar structure. So that means that the vacuum fluctuation and the quantum vacuum fluctuation energy density that we use as a source term to describe the origin of mass and how the vacuum fluctuations occur space-time, this energy is a manifestation that everything is spinning all the time. And why is it spinning? Is it due to, for example, the cosmogenesis? So a way of picturing it, as I described at the beginning, is if a small bubble coming from a smaller scale for example, arrive in the universe and then expand. This expansion, because outside is, if it exists pure vacuum, for example, you just expand, and this expansion creates a loss of pressure, and to compensate this loss of pressure, we see some vortices appearing, because a vortex allows the transition from high pressure to low pressure. There is a gap between the outside and inside. And this is this expansion. We could see it's continuous expansion of the universe is the motor that creates everything spinning. As I said earlier, we can see the other way around. It's the small scale that feed the spinning of larger scale, you see. But there is a constant relationship. This is why Nassim at the beginning was speaking about holographic mass solution, because this holographic principle indicates the relationships, that how the small scale and large scale are in constant relationships and cannot be separated, cannot be isolated. This is why sometimes in physics we see problems or people starting to say, let's consider an isolated system. And Nassim is always saying, it's not possible. As soon as we isolate a system, we just cut the source of rotation, we cut everything. So we have to take into account all those relationships and all those scales all together. But it's difficult to do this, I mean, formally with equations. So this way it's nice also to segment stuff, but we need to keep in mind that everything is in a relationship, and it allows also this source term to exist to feed the spinning and the rotation.
Okay.
Does it answer a little bit your question?
It helps. It helps some. I think I need to try and find some visuals to help me picture this better. But probably fluid
Yes.
flow is a good example that I can look at, and that might help. So thank you very much.
Yeah, no, okay. Thank you, Steve. Have a good evening.
Too.
Bye-bye. Okay. So we're gonna take another questions from Thomas Pianman. So does this potential change? Hello, Thomas.
Can you hear me okay?
Yes, I can hear you.
Thanks for doing this. This is fun.
Nice. I'm glad you enjoy it. So you had a questions about the
The redshift.
redshift. Yeah.
So for a long time, I have
Yes.
intuitively not liked the standard explanation of the redshift as a Doppler effect. And I'm curious if your or Nassim's or your this new understanding in any way comes up with a new story or a new explanation of the redshift. Meaning, do you guys still think of galaxies as moving away from each other at an accelerating rate, or is there do you guys have a different way of thinking about it?
It's a good question. Yeah. I haven't been much involved in this problem, so I'm sure Nassim would have a better answer than I do. But the way we are treating because the redshift in general is also how a gravitational field would modify my perception of light. And this was extensively used by Hawking in his Hawking radiation theory, because he was considering, okay, if I'm outside a black hole and I see a ray of light going to the black hole and then maybe reflect to me, the fact that very far from the black hole and close to the black hole, the gravitational field is not the same. It means that there will be some time dilation, because the perception of the observer that is very far of the distance close to the black hole won't be the same as if I was very close to the black hole. If I'm moving to the black hole, I will just follow the gravitational field, and I will not experience things differently than I do when I'm on Earth, for example. But if I'm very far, the person who will go to the black hole will then start to be shorter and shorter, and maybe will take an infinite amount of time to reach the black hole. But it's only the information that I observe if I'm very far from the black hole, and it's just that at some point we call black hole because light cannot escape. It's just that it takes an infinite amount of time for a photon to go outside the black hole. This is what the theoretical model says. And your questions about if I think if I put your question in terms of galaxy moving away from each other, it means that yes, okay, this is why there is a Doppler effect, because they are moving such that the light that I perceive is not the same wavelengths as it was emitted. Okay. I haven't seen we haven't discussed a different approach of that, because we have been mainly focusing on particles, but we are currently aiming more fundamental work on cosmology also, because now we realize, maybe you have seen it in the papers, we have particle physics, we have quantum field theory, we have general relativity, astrophysics. So there are so many projects, seeding from this very fundamental basis. So then we start to hire people with a good scientific level to, explore those fields. And we are currently discussing with astrophysicists to join the team and to also explore those questions. And I think it's fundamental. And the reason why I was talking about the Hawking radiation is that in particle physics, particle creation, they are created from the ground state. So which means that the ground state which is the energy, what we generally describe as the energy of the vacuum fluctuations, is set the ground state. And then we observe particles created from this ground state. But the ground state is also affected because of this redshift by the gravitational field. The gravitational field of the scale at which it exists. So it's really interesting to understand how the scale affect particle creation and the size of the particles creation and how it is connected to the vacuum fluctuation and to ground state. So it's a bit theoretical, but I won't expand much on it. But this redshift is really important and really fundamental. How the ground state is hiding this notion of scale we have been talking the whole night about.
Mm-hmm.
This was only to say that. I hope it's not too complicated.
No, I think my question is also just an encouragement of an excitement at the degree to which you guys have been, like, having very peripherally been aware of Nassim Haramein's progress over the years. The recent mass of the proton is significant, and I think there will probably be an equivalently significant new story about redshift that will come out of this work, and I'm excited to see what that looks like.
Yeah. Okay. Thank you very much,
Thank you.
Thomas. That's really kind. Yes, we can see. I can see a question from Luca. Are the sessions recorded? Yes, and they're recorded, and you can watch it afterwards on YouTube. And feel free also to ask questions on the YouTube videos. We can also answer them directly online. Maybe we take one last questions. Maybe from Fabrice. I'm sorry for the other people who ask questions. Okay, Fabrice, I can't find you. Maybe Fabrice has left. Maybe we can ask Stefan to come, no? Okay, Stefan. Okay, Stefan, can you hear me?
Yes, I can hear you.
Okay, perfect.
Okay, thank you.
So you were asking questions about Alexander Kasyanchuk. And you were saying that, okay, time is quantum fluctuation like temperature is Brownian motion, time is slower on objects, gravity is time, pressure. Yeah, the way it relates to our work is that, anyway, maybe for the other, I will read the full question, sorry. I am reading the book of Alexander Kasyanchuk, Time Matters. He explains, space-time is regular space filled with time and not four-dimensional surrogate. Time is quantum fluctuations, like temperature is Brownian motion. Time is slower around object, gravity is time, pressure. And Stefan is asking, how does this correlate with your work on quantum fluctuations? The fact it relates to our work, the fact that we describe space-time as a fluid, moving, constantly moving, and the circulation within this fluid, which means the velocity of the fluid particles. Even though for now, for conveniency, we set the Planck scale as a fundamental scale for our reality, but due to the fractal nature, as we said many times today, it's just continue below the Planck scale, but it's convenient to set the Planck scale function of the different fundamental constants that have been measured. And the circulation is a reflection of time. So the fact that everything is moving, the notion of time only exists because of the movement, and this correlation between two different time that makes reality exist. This is what we've demonstrated through the correlation function with the vacuum fluctuations. So yeah, I feel like it's very well connected, and most of the time is hard to understand, because how is it coupled to space? It's just because we have the memory of where we were just before. If I move my hands from there to there, it's just because I remember that my hands was there at some point that now I can say it has moved. But if I'm in the instant, just feel like my hands have been there all the time. So it's also related to the question of memory, how we remember things, how the universe is also remembering, and a way. I don't know how to respond further to your question, Stefan, but if you can maybe precise.
Yeah, I see you focus basically on objects or the tiny parts and the relationships. And in these books, he just describes that time has different speeds in different. The time is not moving everywhere the same. And this causes a lot of effects. And yeah, it's an interesting approach.
Yes,
so
yeah.
I feel it's different from your work, but maybe the two, if you put the two together, you come to new conclusions.
Yeah, we could be inspired. Yes, we could have new ideas. Yes, yeah, and this notion of time is slower around objects. Yeah, comes clearly from, it is embedded in general relativity formalism, but
yes,
it's around very heavy objects. Time is slower, and and it's funny because in French we have also an expression. Maybe it exists in English. Maybe you will let me know. But when we say, okay, this moment is very grave, meaning that it's the noun from gravity. I mean, it's the adjective from gravity. The perception of the moment is much slower, as if the time was like dilating. So it's funny how it has an impact also on the way we speak and we experience things. I don't know if in English it's the same also.
Thank you. Thank you.
Okay, thank you, Stefan. Wow, there are still many questions. I think we're gonna save them and maybe answer them either on the video description or in the comments. Would be nice, so that we can answer all of your questions. I was Yeah, very happy to be there tonight to answer your questions. It's always very, very interesting. Thank you for asking questions because it brings new ideas also. So it's great to ask questions, to give your own point of view, the way you perceive also what the work we are doing. It's very precious and yeah, thank you very much also. And I wish you all a very good day or very good evening, function of where you are. And I will see you in a couple of months. Next month, I think it will be Olivier, then William, and for the last session of the year, it will be Nassim. It's Nassim himself that will do the session. So don't miss the December Think Beyond. And yes, so see you very soon, and I wish you a lovely day, lovely night. Bye bye.